Hello everyone, I'm Watanabe from Keio University. My presentation title is Accelerating ODE-Based Neural Networks on Low-Cost FPGAs. There are two main contributions to this paper. First, we evaluated the accuracy of ODNet, a new deep learning architecture based on ordinary differential equations, on low-cost FPGA devices such as PINC-Z1 board. Second, we evaluated the performance improvement when offloading the Euler method and convolutional operations, which are bottlenecks in the execution of ODNet, to programmable logic part of the FPGA. Recently, performance of image recognition models has been improved. There is much interest in edge AI for anomaly detection and image recognition in recent years. In addition, high-performance models such as GoogleNet and ResNet have been proposed in the deep learning community. These models use a massive number of parameters to achieve high accuracy, and there is a problem that all the parameters cannot be stored in the FPGA due to VRAM capacity limitation. The right-hand side of the figure shows the relationship between the number of parameters in ResNet and the error rate. The figure shows that as the number of ResNet parameters increases, the error rate decreases. The dotted line in the figure represent the amounts of VRAM in the FPGA of the SoC, indicating that even the smallest ResNet 18 cannot implement all the parameters in the FPGA VRAMs. In addition to high accuracy, reduction of the number of parameters is required for implementation for edge devices. ResNet is a deep learning-based image recognition method, and the architecture consists of three components: input, pre-processing, building blocks, post-processing, and output. The right-hand side of the figure shows the building blocks. The advantage of ResNet is that, in addition to the usual forward propagation, the building blocks has a shortcut connection, where the input values are directly added. Therefore, if we assume that the input is ZT and the output is ZT plus 1, and the usual forward propagation is FZT theta t, then this t is added by the shortcut connection, so that ZT plus 1 equals FZT theta t plus ZT. The advantage of using this architecture is that high accuracy can be achieved by stacking layers deeply, since it can deal with problems such as gradient vanishing. On the other hand, it has a disadvantage that the number of parameters and intermediate outputs can be huge in size, resulting in a long training time. ODE-Net is a deep learning architecture using ordinary differential equations, inspired by the fact that ResNet's building blocks can be replaced by ODEs. Comparing the output of the Euler method and building blocks in ResNet, the shapes are almost the same, though there is a constant step size h. The ability to reduce the number of parameters is a primary advantage of ODE-Net and suitable for implementation in edge devices. Here we compare the architectures of ResNet and ODE-Net. For the sake of distinction, we will refer to the building block in ResNet as ResBlock, and the building block in ODE-Net as ODE-Block. In ResNet, the building blocks are stacked, where in ODE-Net, the stacking is replaced by an iteration of a single ODE block. If we assume that the order of memory required for one building block is OL, the required memory is OLM in ResNet, because there are m building blocks stacked. On the other hand, in ODE-Net, the required memory is OL, since the same ODE block is repeatedly used. Ideally, ODE-Net can be implemented with 1 by n the number of parameters of ResNet. In this research, we employ a SoC-type FPGA with integrated programmable logic part and processor part as the target platform. More specifically, we use TUL's PINC-Z2 board, and the table in the slide shows the specifications. This figure shows a concept of our implementation. We assume that only the ODE block is executed in the PL part, and the other computations are executed in the PS part. The ODE block consists of 5 layers: convolution, batch normalization, activation function, convolution, and batch normalization. And these operations are repeated. In order to execute ODE block in the PL part, the parameters theta and feature maps are stored in FPGA VLAN. Assuming that theta is stored in the PL part before prediction, there are two types of data transfer. That is, data transfer of input image from the PS part, and data transfer of output result from the PL part. Please note that PS and PL part are typically connected via AXI bus, and DMA transfer is used for their communication, though not fully implemented in our design. In this work, polarization along the output channel is applied to speed up the execution of ODE block in the PL part. This figure shows an example of a two-parallel case. Convolutional operations compute each kernel sequentially for an input. Since the input does not change, the computation of multiple kernels can be executed in parallel. In the figure, two kernels are calculated in parallel, so the results for two channels are obtained simultaneously. The slide illustrates the network configuration in LessNet. The network used in this study consists of 7 layers: Combo 1, Layer 1, Layer 2 1, Layer 2 2, Layer 3 1, Layer 3 2, and the fully connected layer. The less block used in each layer consists of convolution, batch normalization, ReLU, convolution, and batch normalization, as shown in the right-hand side on the figure. The table shows the resource utilization when Layer 1, Layer 2 2, and Layer 3 2 are implemented in the PL part in this work. The parallelism column in the table shows the parallelism in the output channels. As mentioned earlier, when the parallelism is 32, the timing constraint of the target FPGA board cannot be met, so we evaluated the utilization when the parallelisms are 1, 4, 8, and 16. The resource bottleneck is the VLAN, which reaches 100% utilization when Layer 3.2 is implemented in the PL part. On the other hand, in all cases, DSP, LUT, and flip-flop resources are available. Thus, additional application logic can be implemented in the PL part. Due to the limitation of VLAN capacity, we cannot implement all the layers in the PL part of PinkZ board, but we can implement both the Layer 1 and Layer 2 too. In this work, 3 experiments are conducted to evaluate these implementations and the newly proposed model. The first is the number of parameters, the second is the accuracy, and the third is the execution time. We use Cipher 100 as the dataset. The number of channels, width, and height size of each image are the dataset in 3, 32, and 32 respectively. The number of parameters and accuracy are evaluated in software, and the execution time is evaluated by simulation with a batch size of 1, since we focus on inference only. For these experiments, PyTorch is used for software evaluation, and Vivado 2017.2 is used to implement OD block in the PL part of PinkZ board. We evaluate the case of n equals 20, 32, 44, and 56. 4 models are evaluated. That is, the first model is the LessNet. The second one is ODNet, which replaces the less block of LessNet with OD block. The third one is RODNet, and the fourth one is Hybrid. RODNet and Hybrid are the architectures proposed in this paper. The former is a reduced version of ODNet that heavily uses only one specific layer, which is implemented in the PL part of PinkZ board. This architecture is expected to reduce the number of parameters and improve the execution time by the dedicated circuits. The latter is an architecture that replaces only layer 3.2 of LessNet with ODNet. Unlike Hybrid, IODNet has several variations. RODNet 1N and RODNet 2N are architectures in which Layer 1 and Layer 2 are implemented in the PL part, respectively. In RODNet 1 plus 2N, both the Layer 1 and Layer 2 are implemented in the PL part. This slide shows the network structure of LessNet. In LessNet, after performing convolution in Comb1, Layer 1, Layer 2, and Layer 3 perform rest block with stride 1 stacked n-2 by 6, and Layer 2 and Layer 3 performs rest block with stride 2. Finally, FC execute average pooling fully connected and softmax. Therefore, the output size is halved in height and width and double in the number of channels when input data goes through Layer 2 and Layer 3. This slide shows the network structure of ODE-Net. ODE-Net and use one ODE block repeatedly in these layers while LessNet and stacks multiple less blocks in Layer 1, Layer 2, and Layer 3. Thus, ODE-Net and can reduce the number of parameters compared to LessNet and. RODNet 1 is the architecture of ODNet N, where Layer 2 and Layer 3 removed. On the other hand, the number of execution counts of Layer 1 is increased, and the total execution count of OD block is equal to ODNet. RODNet 2N is a version of ODNet N, in which the execution count of Layer 1 is reduced and Layer 3 is removed. Instead, the execution count of Layer 2 in OD block is increased. RODNet 1 plus 2N is an architecture that combines RODNet 1 and RODNet 2. Layer 3 is removed from ODNet N, and the execution counts of Layer 1 and Layer 2 are increased instead. RODNet 3N is an architecture that removes ODNet iterations and Layer 2. Instead, the execution count of Layer 3 is increased. Hybrid 3N is the same as that of LessNet and except for Layer 3. Specifically, Layer 3 is replaced with OD blocks. This graph shows the number of parameters in these architectures. In LessNet, the number of stacked less blocks is n, so the parameter size increases in proportion to the number of n. In the RODNet variant, the number of stacked OD blocks is constant, while the execution count is increased in proportion to n. Therefore, the parameter size difference is minimum when n is 20 and maximum when n is 56. In the former case, the parameter sizes of ODNet 20 and RODNet 320 are 36.24% and 43.29% less than that of LessNet 20, respectively. In the latter case, the parameter sizes of these two models are 79.54% and 81.80% smaller than LessNet 56, respectively. For Hybrid 3N, the parameter reduction is smaller than RODNet, since all the layers except Layer 3 are used as well as LessNet. When n are 20 and 56, the parameter sizes are reduced by 26.43% and 60.15% respectively compared to LessNet. These graphs show the accuracy of each architecture info network. In this experiment, SGD is used as an optimizer, and L2 regulation parameter is added to each layer. In the training phase, the number of epochs is set to 200. The learning rate starts at 0.01 and is reduced by 10 for every 100 and 150 epochs. Overall, LessNet had the highest accuracy in all the cases because its parameter size is the largest among them. Hybrid 3 is the second highest accuracy after LessNet when n is 44 and 56. The difference between the two architectures is 2.16% when n is 44 and 0.98% when n is 56. It seems that hybrid 3 is robust over overfitting, especially when it is increased. Among the all OD-net variants, learning is unstable except for RODNet 3 when it is 20 and 32. The difference between RODNet 3 and ResNet is 5.48% when n is 20 and 5.70% when n is 32. This difference is larger than the difference between ResNet and hybrid when n is 44 or 56, but the reduction in parameter size is more beneficial. We compare the architectures shown in this slide in terms of execution time. The first one is ResNet, which is implemented entirely in the PS part. The second is RODNet variant, which offloads only the heavily used layers to the PL part and implements the other in the PS part. However, we focus on RODNet 3N because of its high accuracy and stability. The third is ODNet 3N, in which layer 32 is offloaded to the PL part, and the other are implemented in the PS part. The fourth is hybrid 3N. Like ODNet 3N, layer 32 is implemented in the PL part, and the others are implemented in the PS part. Similar to the accuracy, the number of channels, widths, and height of the disk size are 3, 32, and 32 respectively. In addition, as mentioned earlier, the pink Zetsu board is used as the target board in this work. In the PS part, two ARM Cortex-A9 processors are running at 650 MHz, and the operation frequency of the PL part is 100 MHz. We make an optimistic assumption that data transfer latency between the PL and PS part is 1 cycle per float. In the PL part, we use the results when the parameter is 16 to evaluate the maximum performance. This graph shows the execution time when LessNet, ODNet 3, ODNet 3, and Hybrid 3 are implemented in FPGA. A pair of bars are shown for each end. The left bar shows the execution time when using only the PS part, and the right bar shows the result when using both PS and PL parts. In this experiment, for all the architecture except for LessNet, layer 32 is the target layer uploaded to PL part of the FPGA. Please note that in LessNet, the CPU target part is equal to the total execution time since everything is executed in the PS part. From the graph, we can see that the benefit of holding to the PL part is relatively small for ODNet 3 and Hybrid 3, while it is large for all ODNet 3, depending on the percentage of layer 32 in the total execution time. The percentage of execution time for layer 32 in ODNet 3 and Hybrid 3 range from 21.24% to 29.64%, while the percentage accounts for 87.87% in ODNet 3. Therefore, the overall speedup ratio of ODNet 3N is 2.66 times, which is the largest among all architectures. These results show that RODNet 3N can achieve high stability in parameter size, accuracy, and speed. This is a summary of our work. To reduce the parameter size for deep learning-based image recognition methods on edge devices, we focused on ODNet. To implement OD block in the PL part of pink Zetsu board, we propose RODNet and Hybrid while designing ODNet, so that they are suitable for execution on low-cost FPGA devices. To verify the benefits of the proposed architecture, we evaluated them in terms of the parameter size, accuracy, and execution time. For parameter size, our ODNet 3 achieved 43.29% reduction over LessNet 20 when n was 20, and 81.80% reduction over LessNet 56 when n was 56. As for the accuracy, when n is 20 and 32, our ODNet 3 achieved the second highest accuracy and the highest stability compared to other ODNet variants. As for the execution time, our ODNet 3 achieved a high overall speedup ratio. it was 2.66 times faster than the pure software execution when N was 56. These results show that our ODE-Net 3N can achieve high stability in parameter size, accuracy, and speed.